And then good morning and welcome all. It's the first chapter of EE 201. You are section 04. All right. Share. Everyone heard of Tesla? Not the car company, the person. Nikola Tesla. He was from Europe. I believe somewhere in Serbia. Was a brilliant physicist. And he was recruited by a manager of Edison to actually come to America and work for his factory or for his company. Edison at the time was an established business person, let's say that. And he had kind of an unsolvable problem, or at least a problem that was very difficult and neither he nor any of his engineers could solve. Or so the story goes. And then Edison was working at the time on certain technologies. Obviously, he is known as the inventor of the light bulb. Doesn't mean that he actually invented it. He had lots of employees who were working on it, but the credit always goes to the corporation, right? And he was the corporation. Tesla at the time was working with motors, specifically some sort of AC induction motors, electric motor, and that's why the car company chose Tesla as the name, as a homage to the inventor of the electric motor. Anyway, Tesla came over, worked on quite a few problems, and it did a lot of research, and he was able to solve that unsolvable problem. Edison apparently had a bounty or a prize on that problem, and so when Tesla asked for his prize, apparently Edison laughed in his face and said it was just a joke, and he didn't really mean it. He said, "Tesla, you are my employee. This was a problem with the company, and so it's part of your work or job that you do here." Don't know if any of that is true or not, but that's the story that has been passed down. There were actual disagreements between the two of them. That is fact. Okay, that is fact. So Tesla left Edison's employ shortly thereafter. This is all in the late 1800s. And once they had this falling out, Edison did all in his power to denigrate Tesla and the work that he was doing. By all accounts, he was a very petty, jealous, and vindictive personality. Edison, not Tesla. Watch The Big Bang Theory? No one? Okay. One of my favorite television shows. It's about nerds. I'm a nerd or a geek, if you will. And there was an episode where they talk about this. Okay, you should check it out sometime. Anyway, at that point in time, they were working on electrical power generation. So there is a point to this story. Electrical power generation. So imagine a society where we didn't have electricity, right? All you were familiar with were like oil lamps and gas lamps for electrical light. I mean, sorry, not for light. And along comes this technology where people cannot see, at least with like a gas or oil, you are actually pouring some physical substance and you're setting it on fire, lighting the flame, so to speak. Now here's like a electrical wire that's coming and you can't actually see it flowing through, yet light turns on. So people were like nervous. They were afraid, especially because the technicians who would install these would sometimes often get electrocuted. Again, remember, this is like technology is just coming out. Like no one knows how dangerous this is. No one knows how safe that is. And technicians and people were getting electrocuted. They would suffer severe burns. They would suffer damage, sometimes even death. And so people were nervous. People were afraid. What Edison did was he would say that Tesla's AC technology is very dangerous. He would set up experiments and he would show thousands of volts of AC and just electrocute animals. Apparently that was real. There's also a story that goes that he electrocuted an elephant, but I don't think, from all the sources and everything that I've read, I don't think that's true. But he did electrocute, or actually he paid money to other people, like how they have these fake reviewers on Amazon and websites. who get paid to write reviews. So something like that. He would pay a engineer to actually go out and denigrate Tesla, and they would actually catch these animals and they would electrocute them. And then when came time for him to show his technology, instead of thousands of volts, he would just show like 100 volts, and then he would say, "Okay, this is safe." Anyway, that's the kind of thing that went down. So in the late 1800s, a World's Fair was taking place in Chicago. Okay, Tesla went to work for a person named George Westinghouse. Westinghouse, if you didn't know, is still a brand that is in existence today. Obviously, it's been passed over and changed hands many times, but it still makes some consumer electronic devices. So George Westinghouse invested money in Tesla's technology, and they both bid on supplying electricity to this World's Fair in Chicago. I think Tesla's bid came in about $100,000 cheaper. This is more than a century ago, late 1800s. So it's millions and millions of dollars today, right? So Tesla and Westinghouse got the bid. They safely and successfully implemented electrical power supply to the World's Fair. People were like amazed. It's like, hey, we can't even see the wires going in, or we see the wires, but everything's lighted up. We can roam around at night. Again, think about it. Previously, nighttime, nothing's on there, right? Only in the street you might have some oil lamps. Everything else is like, if the moon is out, that's all you can see. So people were amazed, and they saw how safe it is. And then from that point on, AC was the de facto standard. Edison still tried to bid on contracts using DC technologies, but it had limitations. It could not be supplied over long distances, whereas AC can be supplied over long distances very easy and cheaply. If you've ever been in the parking lot of Sprouts out on Madonna Lane, there's a big, huge electrical structure right in the middle of the parking lot. It's for overhead transmission lines that are running all across the mountains, right? So electricity that is transferred and sent over long distances is always AC. The simple reason is you can increase the voltage and set a very, very high value, like tens of thousands of volts, and send it over long distances very easily. Anyway, so AC won, DC kind of lost. The funny part is everything that we use in real life today is all DC. Everything is DC. So the power outlets are AC, but anytime you plug in an adapter into the wall or a plug into the wall, that adapter takes the AC, electrical AC power and converts it into DC. Okay, that's what the adapters do. Now we have mobile devices that have batteries in them. Batteries are DC. They supply DC, not AC. Batteries are all DC. So when you say we are charging it, all you're doing is you're taking the AC electrical voltage and electrical current that's coming out of the power outlet. Your adapter converts it into DC, and that sends it into your device. Okay, so what's the point of this? Well, remember I said the first half of this class deals with DC analysis and techniques. The second half of the class deals with AC. Slight segue and note, for AC analysis, we use complex numbers, complex math. There is a reason we use complex math. It's actually to simplify the calculations. So it's complex math to simplify the complex equations. You all need to be familiar with your calculators and be able to perform complex math on your devices, without which you would not be able to do the second half of this class. Okay, when the time comes, I will again point this out, but for now you just need to know, as engineers, I assume in your field you have already used complex numbers. If you have not, you need to figure out how to use your devices to perform complex math or complex number calculations. Okay, so DC. DC stands for direct current. AC stands for alternating current. Okay, direct and alternating. All this means is that the value of a DC quantity remains fixed with respect to time. So the schematics, so the illustration that you see here are simply schematics or graphs of the value of that quantity. In this case, the quantity is current, but it could be power, it could be voltage, could be any one of those quantities. And all it means is that a direct current or a DC signal, a DC quantity, has a value that is fixed with respect to time. So x-axis, you have time, the value does not change. We use the acronym DC and AC. We do not actually focus on the word for C. C is for current, but if you think about it, we use AC and DC for voltage, for current, and for power. So if we say AC current, it would be alternating current, which sounds absurd. So we simply use the acronym DC and AC. Don't get focused on the actual word, okay? DC simply means that the value is fixed. And alternating simply means the value fluctuates. That's all it means. A DC voltage is a fixed voltage. DC current is a fixed current. Alternating, AC voltage is variable, fluctuating, and AC current is the same. That's all it means. So batteries are all DC sources, right? It supplies a fixed value of voltage, irrespective of what everything else is going on around it. So if it's a 5-volt battery, it will supply 5 volts. That's it. In real life, obviously, the chemicals inside the battery will degrade over time, and so the voltage value might drop. But for the most part, it is designed to be fixed. Any quantity that fluctuates, which is basically everything else, is AC. Even the words coming out of my mouth right now, the microphone picks up those words, right? My vocal tones. It's a sound signal that is captured by the microphone. The microphone is an electrical transducer that converts the sound signal into electrical signals. And so depending on the tone, depending on how I speak, whether I go very high or whether I go very low, the electrical quantity changes. It's all AC. Okay, it's all AC. AC can take many shapes and forms. So just now I was pointing out, it could be very, very small, could be random. So this is a random signal, which is what all signals would be. Then you have square waves. Square. Rectangular. Again, you don't need to note any of these down. This is just, again, we are introducing the topic, so it's just something that students should be familiar with, but it's not something that I would be testing you on. By the way, if you can't read or understand my writing, which I apologize, my handwriting has gone worse every year, even though I practice it. You just let me know if you can't read or understand something. And this is triangular. Okay, you have rectangular, you have square, you have triangular. What is this waveform? Anyone? The one that you see right here in the illustration. It's called sinusoidal. And that's the waveform that we will deal with in AC analysis. Sinusoidal, and it's represented using trigonometric identities sine and cosine. You can see here, 2 cos 2 pi t, right? Again, this is for chapter 5, much later. We get to it in like 6 to 8 weeks, about 2 months later. So don't worry about it now. But again, just understand that chapters 5 and 6 will deal with sinusoidal waveforms. Okay, the value fluctuates, does not remain the same. What is the rating, the voltage and the frequency rating of our power outlets? Should be general knowledge. It's not something that is limited to engineers or non-engineers. Everyone should know what the power rate, what the voltage rating is. Yes. 240 is there, but not in the US. 120 or 110. The reason is when they first set up the power station, it was, does anyone know where it was? The US first power station in the US and in the world? Somewhere near Niagara Falls. Yeah, Niagara Falls. So they chose 100 as a nice round number. Okay, safe, effective. It was enough to actually supply electrical voltage and power. And then they built some tolerance into it, 110. And so 110 could sometimes fluctuate, go up to 120. If you take two phases together, you put them together, you get 220 and 240. Okay, so we will talk about Ohm's law in just a little bit, but V equals IR, and electrical power is the product of voltage and current. P is equal to V times I. You don't need to memorize any of it now, but there's a point I'm trying to make. So electrical power is the product of the voltage and the current. You increase voltage, you increase the power. You increase the current, you increase the power. But when you increase the current, what happens is the electrical losses in the line also increase, and they increase according to the square of the current. So if P is the product of voltage and current, it makes sense to keep the current as low as possible and increase the voltage. Okay, so when the rest of the world followed in their implementation, instead of using 110 volts, they chose 220. So the US is 110 volts and frequency of, anyone know the frequency? It's 60 hertz. And we'll talk about that later too. So this is the US. In other parts of the world is 220 volts and 50 hertz. I believe Japan also uses 110 to 120 volts, but I'm not certain. I haven't been there. The good thing is modern electronics has evolved to such an extent that we don't have to worry about plugging in. Previously we had to worry about the voltage ratings on our adapters and everything, but our laptops, our chargers, everything can be just plugged in anywhere in the world and you'd be fine. If you actually take your adapters, if your eyesight is much better than mine, you can flip it around, you can read the tiny letters, it will tell you that the rating input, all devices will have an input and an output rating imprinted on your adapters. Whether it's your smartphone charger or whether it's your laptop charger, it will have that rating. So the rating will be listed the input. The input will say 100 volts to 120 volts, 100 volts to 240 volts input. So you could plug it anywhere in the world, and 50-60 hertz, anywhere between 50 and 60 hertz. So you can use it in North America, you can use it in Japan, Europe, India, wherever. And the output will be, well, if it's a laptop, it'll be most likely 18 or 19 volts. If it's a smartphone, it'll be 5 volts or 5.1 volt. Anyway, that's kind of general knowledge, but there, again, there's a purpose and there's a background to how we arrived at all of that. Slight segue, an example. Have you ever heard that if you want to install a hot tub, you need to get an electrician to come out and do some installation work? Okay, that work is basically taking two phases of 110 volts and combining them together. So if you take two phases of 110 or 120 volts, you now have increased or doubled your voltage. If you doubled your voltage, you have now increased your power. So hot tubs are something that requires a huge amount of electrical power to operate or to work. And so you need a licensed electrician to come out and install those two phases together. That's what they're doing. Okay, so that's DC and AC. One final note about this slide. We talked about hertz, right? And again, we'll get to that when we do AC. But you see, it's a repeating cycle. It goes up, it goes down, it goes up, it goes down. It's alternating between a positive and negative peak. So even if it just stays completely positive, or it could stay completely negative and fluctuates, it is still alternating. It is still AC. It does not have to alternate between exact positive and exact negative. It could be anywhere. Okay, as long as the value changes with respect to time, it is alternating. It's AC. Okay, 60 hertz, power outlet 60 hertz means that our value goes from 0 to 110, back down to 0 and below 100, below 0, positive, negative, positive, negative, 60 times in 1 second. It seems like a lot, but it's actually not. It's very, very small. 60 hertz is a very low frequency. It's below human hearing range. We can't hear below, they say 20 hertz, but it's like below 100 hertz. Not many people can hear below that. Okay, so 60 hertz is at the very, very low end of the hearing range. The frequencies that we use in everyday life are in the megahertz and the gigahertz range, meaning the value of that electrical quantity changes millions and billions of times in 1 second. It's that fast and that high. Okay. Any questions about this slide? All right, typical electrical circuit. I assume from physics you are familiar with the symbols, but I will still do a brief recap, right? So the three components that we look at in this class are the resistors, capacitors, and inductors. And the respective electrical quantity is a resistance, capacitance, and inductance. Okay, that's the actual electrical quantity. And the physical component is a resistor, inductor, and capacitor. Those are the only three quantities we look at in this class. So resistors are noted by R, uppercase R. All right. Unit for resistor or resistance, ohms, named after George Ohm. And as it happens throughout history, one person gets the credit, but the work has usually been done by like several people. So whatever George Ohm was a physicist, a researcher who was doing a lot of research with voltages, currents, and resistances. And somewhere along the way, he did so much work that it was attributed to him. And so he came up with a law that came to be known as Ohm's law, and the unit for resistance was named after him. But let's be clear, okay? No single person ever does alone the work. The electric motor is attributed to Tesla, but there were so many people who came before Tesla who did a lot of work that he could take and then come up with something new that worked. Okay, so it always works like that. Was there a question? Okay. So again, resistance is ohm and is noted by the Greek letter omega, uppercase omega. Inductor, capacitor. Well, actually, we won't talk about inductors and capacitors now. We'll wait for chapter 3. Let's just talk about voltage. So voltage is noted by V. And typically, we're going to use lowercase voltage. The unit is named after Volta. Volta is an Italian physicist, I believe. And so it's volt. Short acronym was uppercase V. Current is noted by I, named after ampere. So ampere. And again, short form is amp or simply A. How about power? Electrical power? Yep. Watt? James Watt. Uppercase W because lowercase w is used for work, energy. So uppercase W. All right, so these are the quantities that we'll work with. Okay. Voltage, current, power. three physical components are resistors, inductors, and capacitors. The electrical quantities are voltage, current, and power. All right. Then, if you see the circuit, we are saying that this is a source, right? So any component, any physical device that supplies energy is known as a source. We'll talk about sources in the next slide, but anything that supplies energy is a source. Anything that consumes energy is a load. So in our class in 201, it's a voltage source and a current source. Everything else is a load. So resistor, inductor, capacitor are just loads. They simply receive the energy. They do not independently supply their own energy. Okay. And the wires that you see in there are known as conductors. Conductors are used in an electrical circuit to make connections from point A to point B. Without a conductor, there would not be any current flow. Okay. Current needs a pathway to flow through. Again, current always flows through, voltage is always across. So current needs a fixed loop to flow through. So all of this is a conductor. Okay, everything is a conductor. Now, keep in mind that this is simply a circuit schematic. It is not real. Well, when I say not real, as in it's not describing the actual length of the real conductor. A conductor is anything that conducts electricity from one point to another point. So this USB cable is a conductor because it's conducting electricity from one point to another point. This HDMI cable is also a conductor. All conductors, by their very nature, have resistance, inductance, and capacitance. It's just that the value of those resistances and inductance and capacitance does not rise high enough to the level of interference. So in real life, I could take an HDMI cable, which is about 50 feet long, and I connect it to, let's say, a source here, and I send it to a building across to connect to a TV there. Do you think it would work? Maybe, but there will be some signal loss. Okay, just because an HDMI cable will have some resistance, will have some inductance, will have some capacitance. And digital signals, by their nature, are all or nothing. Meaning if the signal reaches, then you have your data transmission. If it's weak, then everything is lost. Okay, so a 50 feet HDMI cable would be very, very expensive, to be built correctly, keep a resistance low. But if I was to take the same HDMI cable and draw it theoretically here, then a dot would be the same as a small dash, would be the same as this line, would be the same as that line. So all three of them would have 0 ohm resistance. And the important point here is that all calculations, all analysis that you do in 201 is theoretical, meaning a resistor, if given to you, is 10 ohms, you would use 10 ohms. A conductor has 0 ohm resistance. You do not worry about the resistance of a conductor when you're trying to solve a problem. Conversely, when you actually take the lab and you actually perform this exact same circuit and you analyze it, the resistor, because of temperature variations, pressure variations, if it's a 10 ohm resistor, the actual value of the resistance might be 10.1. It could be 9.98. It could be something else. If it's gone really bad, it might be like, 8 point something, which happens sometimes. The chemicals inside the resistor would degrade over years. It would take a long time, but it would degrade. And so instead of being like 10 ohms, it would be like just 8.9. A conductor, as I was just saying, a real life conductor, a cable, again, would have very, very low resistance, sometimes even so small that we cannot measure it. But conducting leads or wires or cables actually have some resistance. So it would add like 0.1 or 0.2 ohms. So you would have to take that into account when you are performing an experiment in the lab. But as far as 201 goes, all conductors are 0. All right, let's take a 10-second pause, think over all of this, and let me know if you have any questions. All right, so what is circuit analysis? Circuit analysis is simply the study of the techniques and the methods to determine the values of the unknown electrical quantities in a circuit. You have a source, the source is supplying energy to these components, whether it's voltage or current or power. These components, when they're connected, depending on the manner that they're connected in the circuit, will receive some voltage, will receive some current, will receive some power. So our job as the engineer is to analyze the circuit and determine what the values of those voltages and currents would be at any given point in the circuit. So circuit analysis is simply the study of the techniques and methods to determine the values of these unknown electrical quantities. And that is what we'll learn in chapters 1 and 2. Okay. All right, sources and loads. Anytime you see a circle, oh, one final thing about the circuit schematic. The circuit schematic can be drawn anyway, right? It's on paper. Typical configuration that I've seen over 30 years, the source is always on the left and the rest of the circuit is on the right. That's how it's typically drawn. But this exact same circuit can be drawn like this. Take a few seconds and take that in. It's exact same circuit. There is no difference. You have a source, voltage is a plus and a minus, plus point goes to a resistor, which is on the left right now. From the resistor, we go to a capacitor, and the capacitor N also goes to the minus of the source, which is what we see here. The minus of the source goes to the other end of the capacitor, which goes to that resistor. The junction point of the first resistor and the capacitor, which is right here, top right here, 1. This is 1. This is 2. This is 2. And you have the other resistor and inductor in series. So schematics can be drawn any which way. You know, once you have the actual components in front of you on a desk, you can connect them however you want. Similarly, the circuit schematic can be drawn any different way, but electrically speaking, it's exactly the same. There is no difference. I could draw this entire circuit lying on its side this way, or the voltage source on this side. Doesn't really make a difference. Excuse me. So, sources and loads. Anytime you see a circle, I know it's not a circle, but it's supposed to be a circle. Anytime you see a circle, it notes either a source or a measurement device. A measurement device is also known as a meter, right? A meter. If it's a plus or a minus, it signifies its voltage. If it's an arrow, it notes a current. Okay. And again, you can draw the schematic any way you want. Plus and minus, plus on the top, minus on the top. It could be on the side, it could be horizontal, plus and minus on the left. The arrow could be pointing up, could be pointing down, could be pointing right, could be pointing left. similarly to the current. So it's a source, it's supplying energy. Measurement, or known as a meter. So if you have an arrow that's at an angle inside a circle, it notes that it's a measurement meter. That came to be because of the first meters that were developed that were analog and had a needle. So needle moves and tells you what the quantity is, or the value of the quantity, sorry. And that's why you would see, but you would not see this in 201, not a lot. This is just something as knowledge you should be familiar with. If you see something like this, it notes it's a meter. If you're measuring voltage, it's known as a voltmeter. If you measure current, it's known as an ammeter. When it measures power, it's known as a wattmeter. Don't know why, but it's also known as a power meter. If it can measure multiple things, more than one, then it's known as a multimeter. And when digital ones came out, they came to be known as digital multimeters, DMM. Now you can buy handheld digital multimeters for like $5. So that cheap. And they're still pretty good, accurate. All right, any questions? In real life, a voltage source and a current source are one and the same thing. There's no difference. It's the same box. When you, if you're taking 251, or whether you take 251 or not, anytime you see a power source, like a DC power source or an AC power source, it can supply voltage as well as current. You cannot have one without the other. Voltage cannot exist without a current, and a current cannot exist without voltage. If you're supplying voltage, you are supplying current. If you supply current, you are supplying voltage. Okay. The difference is in the mode of operation. If the value of the voltage is constant, and now I'm not talking about DC or AC, okay? I'm just talking about the value of the voltage with respect to the value of the current, okay? If the value of the voltage is constant, you are running in constant voltage mode. The current will change according to the requirements of the load. It would be known as a voltage source. Conversely, if the current is maintained at a constant level and the voltage changes according to the load's requirement, now you're running in CC mode, constant current mode, and we say that the supply is now working as a constant current source or a current source. That's all it means. So a voltage source supplies a fixed amount of voltage. The current can change in value. And a current source supplies a fixed amount of current. The voltage can change in value. Again, do not confuse this with AC and DC. This is only with respect to voltage and current. That's it. So in real life, a voltage and current source are the exact same physical box. Ten-second pause if anyone has any questions. Okay. Anyone familiar with the diamond? Right. So this diamond notes that it is a dependent source. Okay. Diamond notes that it is a dependent source. The circle is independent. An independent source, which is the ones that we're dealing with for the entire course, will supply its rated voltage or current irrespective of what is going on around it. It does not depend on anything. Whereas a dependent source is a portion somewhere in the circuit or a point somewhere in the circuit that supplies a rated voltage or supplies a rated current, but it is dependent on some other part of the circuit in order to supply its rated value. Okay, So a dependent source, again, depends on some other part of the circuit to supply its rated voltage and current. It's not like, it's mostly used for theoretical and analysis purposes. Okay, it is part of your 201 course. For the most part, you might either do like 1 or 2 problems on it, but for the rest of the class, we will just work exclusively with independent sources. But this is, again, something that students should be familiar with. You will use this in analysis of like electronic circuits sometimes. Okay, you won't encounter it that frequently. All right, I don't have anything particular to talk about in this slide. I just like the meme. And sometimes I use it for like if I'm doing like a high school presentation to get students, familiar with this. But we have the 3 Thors: the resistor, capacitor, and the inductor. That's the ones that we're going to use. We might use not use, but we'll look at transformers a little bit because they are an extension of a inductance. So you have 2 winding coils wound together, and that becomes a transformer. A transistor is an electronic device. We would not study it here. We would study this in EE 321. If you are required, or if you are thinking about this, so a slight segue. If you are required to take 321 or are thinking about taking it as an elective, it is a direct continuation of 201. So 201 ends and we pick up with electronic devices in 321. I am teaching 2 sections next quarter. Look at the schedule. If it fits in your schedule and you would like to take it, the format is exactly the same as this class. So is the access code and the book. Okay. You would not need to purchase a new code for 321. The one that you purchased for 201 will also work for 321. Okay, let's get back here. Unit prefixes. I do not expect students to memorize all of these. Even I don't remember, I see these every quarter. Obviously, I have the table, I built the table, but I don't remember down the bottom 3. Atto, Zepto, Yocto, even I don't remember. For the most part, we'll be working right here. Okay, everybody's familiar with the millimeter, right? Now, as engineers in your own field, you are used to working with very large quantities and very small quantities. Doesn't matter what field of engineering you come from, right? So everybody's familiar with the millimeter, how small it is. You see it on a ruler, on a scale. You take 1 millimeter and you divide it into 1,000 parts, and you get, so 1 millimeter is 10 raised to minus 3 meters. 1 millimeter divided into 1,000 parts, you get 1 micrometer. 1 micrometer, which is 10 raised to minus 6 meters. 1 micrometer is also known as a micron, hence the name of that company, Micron, because it works in microchips. To give you an idea of how small it is, a human hair, not that I have much left, but a human hair is on the order of 70 to 75 microns. So 1 micro is smaller than a human hair. You take 1 micron and divide it into a further 1,000 parts, you get 1 nanometer. Think about it. 1,000 part of 1,000 part of a millimeter is 1 nanometer. 10 raised to minus 9. And the feature sizes of microchips nowadays are even smaller than 1 nanometers. It's just incredible. And that's the reason why if you go work in a semiconductor facility, you're gowned up from head to toe in white bunny suits. That's what we call, that's actually what they're called. They're called bunny suits, white clothing. You ever seen those pictures or videos, right? You're gowned head to toe. That is not to protect the user. It is to protect the environment from the user. So humans, we shed a lot of dust particles, we shed a lot of hair, we shed a lot of body parts. So all of those, even though they are very tiny and we cannot see them, they are like huge boulders or rocks to the microchips. So imagine if a huge boulder or landslide takes place on a road, everything is blocked, right? You got to repair it. If you're building a microchip, something like that happens, there is no repairing it. You got to throw it out. How about on the other side? Mega, giga, tera, we use those words, we throw them around, right? It's very common nowadays. We talk about gigahertz and megahertz frequencies. 2.4 gigahertz frequencies, the most common one. The FCC opened up the frequency band spectrum for 2.4 gigahertz a few years ago. So cordless phones, wireless cordless phones that plug into your landlines, which no one has nowadays, they run on 2.4 gigahertz frequency. Microwaves, your wireless routers, everything ran on 2.4. Got so crowded, FCC released another frequency band, 5 gigahertz. Routers started having dual bands. You got dual band wireless routers, which have 2.4 gigahertz and 5 gigahertz. All it means it's broadcasting frequency at those points. Anyway, giga and mega. The example I always like to use is time. Mega is a million, 10 raised to 6. How much? Take a wild guess. Tell me how many days, weeks, or months is 1 million seconds without looking it up or calculating. Take a wild guess, as wild as you want. 1 year, a week, anyone? It's less than 12 days. It's about 11.5 some days. How about 1 billion seconds? It's 31 years. 31 point something years. It's closer to 32 years, actually. Now imagine instead of seconds, you had $1. That's the difference between a billionaire and a millionaire. Something we can only dream of. And maybe if you're successful, someday you'll remember. So if you had $1, you spent it every second, it would take you 31 years to run out of your money. That's how much it is. And as a segue, I always like to give the example of a movie that I enjoy. It's called In Time. Anyone ever hear of that movie? All right, good. So I like that movie. I enjoy it. It's got Justin Timberlake in it. It always gets a few laughs. The concept of the movie is this. Instead of money, people have time. From birth until 25 years, you age normally, and everybody ages normally. When you reach 25, there's a clock in your hand, in the body, that starts ticking. And so people have to earn money. I'm sorry, have to earn time. They don't earn money, they earn time. So you go to work and you earn time. You get paid in time. And so it's kind of like a analogy between how what goes on in the world, where poor people are living paycheck to paycheck. So they work so hard, yet they are not enough. There's not enough time for them to live. And if you run out of time, you're dead. And so I like the movie. I like the story, the premise that it's based on. I even enjoy the structure of that movie. So if you have time, you're bored one day, check it out. All right. We will stop. Yeah, let's stop here. I'll pick up here on Friday. I'll be in my office for office hours. If you have any questions, you let me know. Otherwise, you have a good day, and I will see you all on Friday.